always finds a way. And there's nothing wrong with that in nature, because a snake doesn't have the negative connotation that we get from the Bible, okay, and Genesis and stuff. So it's nothing bad about it. I just like the idea that the snake always finds a way. So you can get around a lot of things with bureaucrats, although tenure helps. Okay, so today is supposed to be a recitation. Do you have questions on what you've watched? How far are you doing the reading as a group or not, individually? So most of you should have gotten into adhesive bonding, gone through cold welding, right? Okay, and now adhesive bonding is I think that's the next one. So what are the two things for the next 10 lectures that you're going to be watching, or the first 10 lectures? What are the two things that limit joining?
Surface contamination.
Surface contamination and surface roughness, okay? People started to understand this about 80 years ago, so far as that goes. And there's lots of examples if you think about it. And one of the things you have to do to get rid of both surface contamination and surface roughness, in cold welding, you can't just push two things together. You'll never get rid of all the asperity contact. You'll always have porosity. Even if the material starts deforming, you'll still have voids at the interface because of the surface waviness and roughness, okay? And in fact, if you take something that has no surface contamination, like pure gold in an ultra-high vacuum, and you squeeze two very flat surfaces, you think very flat, apparently flat surfaces together, all the way to the point where you deform them, you're going to get about 1/2 the strength of the regular gold. And the reason is you've got 50% voids on the fracture surface, on the surface, the interface, the original surface. So one of the things you have to do is the straight normal force pushing things together will not cause them to bond. You need to get shearing, sliding contact. And you should have seen probably an example of bonding aluminum wires. Aluminum has a terrible surface contamination in terms of the aluminum oxide is extremely stable. This is a piece of tantalum, but they join these wires together, or these bars together, before they're drawing it into tantalum wire by just squeezing them together, and they cause it to shear. And they do this about 7 times. So there's one of those you can pass around. Here's the bar after they ground the flash off, and they're about ready to draw it through the drawing machine, okay? I don't have aluminum like that. I haven't ever seen aluminum actually drawn in a shop where I could get it. Mostly this is I go through a plant and I say, hey, can I have one of those samples? Okay, most of the time they'll give it to me. That's tantalum. That's a plant over here in Newton, Massachusetts, which is sort of a spin-off of MIT Mechanical Engineering in a way, in that right before World War II, the people at MIT in mechanical engineering developed a way to produce a high-rate vacuum system using steam injectors. Anybody know what a steam injector vacuum pump is? Anybody know what a venturi is? What's a venturi?
It's a tube that changes diameter in the center and then opens back up.
Right, and so if I have a venturi that I'm shooting steam through, and the steam will be coming out at supersonic velocity. It's called choked flow. It's limited by supersonic velocity. But you got a venturi like this, and you got the steam shooting out like this. And if you actually have an opening in the venturi like this, it will suck that high velocity gas shooting through here, will suck gas in this way, and you actually can get vacuum pumps. A big vacuum pump just uses lots of high pressure steam going through a venturi to create a suction. And so the guys in mechanical engineering invented this process, and that was the beginning, right before World War II, of vacuum metallurgy. And so this department kind of took that invention, and during the Manhattan Project, in the basement of Building 8, they were working on things like uranium, okay? In my old thesis advisor, who was an old German, John Wolfe. Of course, during the war, he wasn't allowed to know anything about these types of things. Most people weren't supposed to know about it. But he knew there was something important about uranium, so he said one time at a, was this in one of my, you haven't heard this story, okay. So he was at a cocktail party one night, and he had been studying impurity elements in oil around the world, okay. Vanadium is an impurity in oil, and he was kind of looking where could you get some of these rare elements and stuff, and it turns out we were starting to use lots of oil in the world. And vanadium is another story that he told me as a freshman. But in any case, uranium, there's a little bit of uranium in oil too. And he knew there was something important about uranium, but he didn't know exactly what. So he just mentioned one time at a cocktail party with a bunch of faculty one night that there's a lot of uranium in the oil in the Balkans. And the next morning, 2 Secret Service agents were in his office asking him what he knew about uranium. Okay. Later on, he found out what was important about uranium, as everyone else did. Any questions about surface contamination, surface roughness? This is another example. This is called a friction weld. In a friction weld, you take one bar and hold it, and you spin another bar and you squeeze the two of them together. And if you go online on YouTube, you can see these nice little pictures. And just the heat of friction, this thing will start to glow red at the interface from the frictional heat. You squeeze it together, you forge it, and if you look carefully, this thing is deformed. Not much of an artist, but anyway. There's your interface between the two, and you can see on this thing, the things are squeezed and deformed. It's a forge weld, but the heat is generated by friction. So why is this important? Well, first of all, virtually every steel drive shaft on every car, at least 20 or 30 years ago, was made by this process. You've got the universal joint, the universal joint in a car. You got two kind of forks at 90 degrees with a little cross piston holding them together so the thing can articulate, right? So you got a universal joint, and the ends on the shafts are friction welded to the shaft. They hold the little universal, C piece, bring the bar in. When a friction weld is working well, it makes very inexpensive, no filler metal, not much surface preparation, very inexpensive, very reliable joints. When it's not working well, when the parameters aren't set up for the right pressure and feed and speed of rotation and all these other variables, it makes scrap very quickly, okay? But if you got it working well, and keep your machine operating within certain parameters, it's a very reliable process. If you go up here to Lynn, Massachusetts, they take, or they used to, I guess they're closing, General Electric's closing it down, but they take 2 big titanium discs for a jet engine to make 1 titanium disc by friction welding. So we're talking about something this big around, and you're talking about taking 2 $20,000 or $30,000 parts and turning them into a $75,000 part. So you don't want to make a lot of scrap then, okay? Because each shot's, there's no way to repair it afterwards, okay? It's just scrap. So that's another friction, another.
In your lectures, you talk about shear all the time, and not quite clear what that is as it pertains to weld.
Okay, well, shear is just a shear force. I can have a normal force or a compressive force just pushing down on the table. Shear is sliding across the surface. I have 2 surfaces, and I shear the 2 of them, okay? So the shear I'm talking about, S-H-E-A-R, okay? Mechanical shear. And you have to have mechanical shear because just squeezing together just traps the contamination. You've got to use shear to get rid of the contamination. That's why on the friction weld, you're just spinning it real fast. And at the very center of that, if you actually look at the actual heat-affected zone of the weld, it'll be hourglass shaped because the very center is getting no spinning, 0 velocity at 0 radius, right? So you actually see the shape of the weld. You got to have a little extra force, get it hot, forge it together, squeeze it out, push the contamination out. Whereas the cold weld, the tantalum wire I showed you, that's just shear pushing them together, squeezing out the contamination. And that tantalum oxide is more stable than aluminum oxide. So it actually, tantalum's different than aluminum in that aluminum will dissolve its own oxide. It will not dissolve oxygen. Aluminum metal just doesn't have any solubility for oxygen. Tantalum, you get up to 900 degrees centigrade, and it's like titanium. It will dissolve